This problem says convert the equation from rectangular form into parametric equations. So let's just take this first one, for instance, here, this number a. Y equals 3x minus 4. Now essentially this really isn't too bad to do. It looks horrible and you look at that and say, you don't even know where to start. But I can simply do this. I can say my x equals t. And then from that, my y is going to equal 3t minus 4. So there we go. That's the set of parametric equations that gives me that line. I mean, I could get a little more fancy if I wanted to and change things a little bit more. I could say my x equals 2t minus 3. And then try to find out what that would be for my x here. So I just plug that in for my x there. So then my y would equal 3, and then for x I'm plugging in 2t minus 3 minus 4. So essentially I just took this right here, subbed it into there from that equation there. Hopefully that makes sense. Okay, and then my y would equal 6t minus 9 minus 4. So then my two equations are going to be x equals 2t minus 3, and my y would equal 6t minus 13. So again, I just gave you two sets of parametric equations for that first equation there. So that's really how easy it could be to do these. Now, one thing I like to do is I like to stay in terms of like the powers of the letters. So for instance, what I mean here is, look, that was linear, that was linear. So when they're both the same degree in a sense, they're going to be lines. So then when I look at this one here, this is a quadratic here. So if my x equals t, then my y is going to equal t squared plus 3. And again, I can change this very easily and call x something else, and I would just sub it in there. I can call it e to the t, couldn't I? I could. Now again, keep in mind when I'm actually graphing these or actually thinking about the transformations of these, my domains could change. So just kind of keep that in mind. Because if I look at this x right here, it could be negative or positive number that I plug in that I could get for my x, excuse me. But if I had like my x equaling e to the t, now this x right here, because it equals e to the t, could never be anything negative. It couldn't even be 0. It would have to be greater than 0 just because of what the function e to the t does. And if we think about the graph, it would just do this. So therefore, my x could never be negative. So that's what's kind of strange about these sometimes. So when I say we can pick anything we want, we do have to be a little careful because we do end up with some domain restrictions if we pick certain things. But we could pick something like that and get a line on an interval, let's say greater than 0 to infinity, then I would be okay with that. But that's just an idea of what we could deal with. And again, I could pick something else for x that's linear. I could pick x plus 3, x plus 4, or 2x minus 1. Those are all lines, which would be representative of just my x. Okay, so let's move on to this third one now. This one seems a little more interesting here. The idea we're using here is the idea of this. I always go back to this, sine squared t plus cosine squared t equals 1. So what could I plug in for x here that would give me such a result? Because remember, when I said we're dealing with circular things, we use combinations of sines and cosines. Another thing that might be helpful is this. Let me rewrite this equation. So this is really x over 2 squared plus y over 3 squared equals 1. So what I could do for this one is I could say, hey, because if I think of this equation here, this is really saying sine of t squared plus cosine of t squared equals 1. And if I kind of put these two ideas together here, I can say x over 2 equals sine of t. And I could say y over 2, well, not 2, 3 equals cos of t. And then from there, I can get my x equals 2 sine of t, and my y is going to equal 3 cos of t. So there's my actual two parametric equations I can come up with. So that's kind of the idea when I'm dealing with anything circular. So if I was even dealing with a circle, right, these would be the same numbers underneath or equaling some r squared, and it would result in the same sort of idea that I would use there. One thing to really look at with this problem here is that just the simple sub that we'd have to do with these. But we'd have to understand this idea then. And we're actually we're bringing in another idea that doesn't seem like it relates directly until we start to play around with it. But there's our answer for the third one. And again, we can still come up with variations for this one. I can call x 2 cosine of t, and then I could call my y 3 sine of t. Now that would just change my direction. Now that's the other thing we got to consider when we're dealing with these equations here. When we're dealing with the rectangular form, that's supposed to be rectangular, not regular form. Okay, so there I fixed it. I put rectangular in there instead. Wrong word I had written there. So anyways, so there's my sets of two parametric equations that I get for the last one here. Now again, don't forget about we do have orientation on these too. So which direction are we going in when we graph these? For instance, if I think of the second one here, I do know that if I just graph the equation here, that means I'm moving up 3 and it's opening upward, so it's doing this. Okay, now the thing I don't know is once I introduce these parametric equations into the picture here, there now is a direction. So for instance, when I plug in 0 for x, I get 3 for y. So that's going to be the point. And then when I plug in the point 1 for that, so that's going to be, my x is going to be 1 and my y is going to be 4. So that's going to go up 1, so it's going to be here. So what's going on is we're actually going in this direction. So that's what is a little bit different once I introduce these parametric equations. I still deal with the same picture, but with this picture I now have an orientation. So a direction which I'm traveling in a sense. So there is the 3 problems I came up with for you.